Okay, so welcome to this tutorial, which is titled Knowledge Engineering in Planning, Representation Method. So in this tutorial we will dig a bit into the aspects which are related to knowledge engineering. So the way, the tools, the techniques that you can use for create a model for a planning system and for a scheduling system. And we will also see how much the way in which you encode the knowledge, so the model that you create, affect the performance of the solvers, so in this case of the planners, that will be used for solving the actual problems and the actual test. So for this tutorial, I'm Mauro Vallati, so I will start with the introduction and some parts of the tutorial, and then I will pass the token to Lukáš, which will guide you mainly into the reformulation aspects and into the aspects which are most related to the planners. So this is basically the table of contents, so what we will see and what you will see during these 3 hours, which sounds scary, maybe. So okay, a bit of introduction at the very start, then we will see some languages, mainly for planning, or actually only for planning, I think, and a very brief overview of the state of the art of planners, so what can you use out there. Then we will dig into the aspects of knowledge engineering in planning. So what is knowledge engineering? What are basically the different steps that you have to consider? What's the state of the art of knowledge engineering in planning right now? And what are the issues that we will have very likely to face in the next few years? And then we move into domain knowledge for planners, in which we will mainly focus on how you can reformulate automatically a domain model in order to improve or reduce the performance of a given planner. So the different way in which you can re-represent your PDDL, in this case, models, with the main aim of helping actually on performance. Then we will move a bit on the boundaries of the main focus of the tutorial. So rather than thinking about the usual way in which knowledge is engineered, so you have a human expert which is sitting down, is using some tool and is coming up with his own view of encoding, we will see what can be done automatically or using what is usually called the crowd for encoding for you. And then we will give some conclusion and we will highlight some challenges for the future. So for starting then, it's always useful to remind ourselves what is planning and why is it important. So starting from a very, very, very high level, we can say that planning is a pivotal level, is a pivotal element of what we call intelligence. So we don't know actually what is intelligence, so we don't have a definition of intelligence. We know how an intelligent agent may act, but what we know for sure is that for every intelligent agent, planning is needed. And what is planning is basically the synthesis or the generation and execution of plans, where a plan means that you can reason with action, information about the world, which are given to you usually as the initial state in which you have to operate, and the goal that you want to reach. And the main element is to put together actions for generating plans. So given the initial state, you synthesize a plan, which is a sequence of action that lead you to the goal. And on the matter of actions, actually, yesterday we were in a restaurant and I got a fortune cookie, which told me, which gave me another motivation why planning is important. Because basically actions, as they said, is the basis of success. So if you need something which is not a scientific support for the importance of planning, I think you can go in a restaurant and grab one of these cookies, and that will give you another motivation for keeping and working in this area. And let's focus a bit on the main assumption of what is termed domain-independent planning. Because let's say in AI or in planning, we can focus on two main areas, which are domain-independent and domain-dependent. Where for domain-dependent, you usually have much better performance, but you are developing something which is focused on the specific application on which you are working. So let's say from a scientific point of view, you are not really pushing too much the edge. You're not developing something which is groundbreaking, or that can be used easily in different domains. While this is exactly the goal of domain independence. So you are developing some techniques which are general, so which doesn't need any specific knowledge of the application, and you then try to improve them in order to make them, let's say, efficient and effective for a wide range of possible applications. And for this reason, you need a logical separation between the domain model, which is the way, or actually the formal specification of the knowledge from the domain, and the planning engine, which is the solver, which is the piece of software, or even the human if you want, which can reason upon the knowledge which is provided under the form of a domain model, and which can then provide the plans for solving your problems. So you have this sort of clear separation. On the one hand, actually, you have the application domain, which is not formalized. So it can be, I don't know, let's speak about logistics. The idea of the logistics area is the application domain. So you know there are tracks, you know there are depots, you know that you have to move things around, but you don't have a formal model. What you need to do in order to start planning is create the formal model, which is called the domain model, and then provide it to the planning engine in order to be able to reason. But this separation, the separation between the reasoning side, the reasoners, and the model, is the basis of a domain-independent planning. And it's also the basis of what we will see later about knowledge engineering and about reformulation. Because if you have something which is specific for an area, for a domain, you don't actually need to exploit these sort of techniques. And what are the strengths and the weaknesses of these very important assumptions? So we have a number of positive implications. So, okay, on the one hand, we have that this assumption tends to make planning different from planning and scheduling in manufacturing, because it is at a much higher level, and you can reason basically with any sort of planning. We have example of application of planning for creating music, for controlling traffic. So you are making a very strong separation. Basically, given this assumption, you can use planning every time you need to reason about what to do and when to do it in order to achieve your goals. And the other very important point is that since you are decoupling planning engines and domain models, you can basically develop, test, debug, validate, or substitute any of these two components without changing the other side. So if you have a PDDL domain model, for instance, PDDL model, and you decide to use fast downward for solving your problem, and then at some point you realize that it is generating some plans which have some qualities that you don't like and you prefer something different, you can change the planner and use, I don't know, Llama or Madagascar or something different without changing the PDDL model. And the same thing the other way around. If you decide to modify the PDDL model in order to catch some different behaviors of environment, you can do that without changing the planner to some extent, if you're not using different features of a PDDL. But we will see that later. And the last point, the last point is that basically, since you have a formal model of a knowledge, which comes under the form of this domain model, you can use that model not only for creating and generating plans, but you can also use that model for other functions not directly related with planning. So you can use it for validating a plan which has been generated, for instance, by a different approach, or you can try to use it for some mining and machine learning purposes, or for conformance checking, for instance. So the fact that you have a formal representation, which is decoupled from the reasoning side, allows you also to exploit this model for different things. Clearly, these are the positive implications. We have also a number of negative consequences of this assumption. First of all, and if you have taken part or if you have read something about the IPC, the International Planning Competition, you should be very aware of this. Basically, it's not a matter of, okay, I develop a domain model which is handling all the features that I want from the real domain, and then I select a planner. No, usually when you are developing the domain model, you are still restricted to use a representation which is supported by what planners can handle. So there is not really they are not really decoupled from this perspective. And the other point is that clearly, since from the reasoning side you don't have specific information about the domain, your performance are affected by this. So you have some sort of inefficiency because you are reasoning, you are performing some reasoning with some very high level, with very general techniques, while you might use something which is specific for the domain and getting much better results, clearly. And one thing that is probably important to highlight is that you have a domain models, you have a planners, a lot of work has been done on improving these domain independent planners, so the planning side, also because of the international planning competition, which I was mentioning before, which was pushing this developing a lot. But on the other side, we are not paying enough attention to methods and tools for producing good domain models. And clearly, you need both a domain model and the planner for reasoning. And this is something that seems to be basically undertaken in some way. So there is not a lot of work which is focusing on this area, which is kind of a shame. And yeah, that's for summarizing a bit the different perspectives which are involved every time you are speaking or you are considering a domain model. This is some sort of an overview which is taken from a work from McCluskey and Porteous, I think from 2009, something like that. So you have a domain model in the center, right? And then you have two different and actually conflicting perspectives. Because on the one hand, from the modeler side, from the human side, what you want to do is to have something which is human readable, which is easy to validate, to maintain, that basically doesn't need documentation. So you can read the model once and understand what is going on. On the other hand, you have the planner side, so the reasoner side, which is instead concerned about efficiency. Another aspect like correctness and completeness of the planner's algorithm. So the thing is, while you as a human are more concerned about being able to understand, extend the system, from the planning side, the planner is only concerned about producing something which works and producing something quickly. And also you have some sort of shared concern between these two perspectives, which include the plan quality. So you as a human are encoding the knowledge in a way in which you believe good plans can be created. They must all be valid, but you may have some preferences on the shape in order to define the quality of these plans. And this is also a concern which is shared by the planner. And so one point which can reduce basically this fight between the human modeler and the planner is the extraction of the domain knowledge, exploiting reformulation, which will basically provide to the modeler a good perspective of the domain model. So you keep your original domain model that you have developed, you exploit the reformulation, so you change the way in which the model is represented so that it becomes more planner friendly for generating some plans, and so everyone is happy. In some end, the modeler can still read the original domain model, and the planner has something which is easier for it to reason upon. And yeah, and now Lukáš, it's your time to solve.
I mean, in order to somehow encode the knowledge, the domain model, we need a language where we can model the knowledge. And I mean, since we are an ICAPS community, we very likely all know PDDL, the Planning Domain Description Language, which actually has been developed for the first international planning competition, which took place 1998, so it's nearly 20 years ago. And I mean, because basically that language was used for basically all the other editions, so that we somehow got some evolution of this language. I mean, interestingly, PDDL 1.2, which is basically one of the first one, so it's Well, it uses a predicate-centric representation, which, for instance, if you know the notion of classical representation, that the environment or the world is represented by predicates. So, which means that you somehow specify the relation between objects, like, a robot is at some location, or the robot carries a box, or whatever. So, interestingly, then, besides the, let's say, classical strips representation, which basically you have only predicates, you have just positive preconditions and add and delete effects, just the basically most simplest representation. So that it already offers some extensions, which we call ADL. So we could specify this called conditional effect. We could use some quantify preconditions, or we can have disjunctions and so on. And even more interestingly, so in that edition, we could specify what is called the domain axioms, which are some invariants that hold in the domain model, and also we could specify hierarchical actions. So for those who are familiar with HTN, where basically we can have some primitive actions that are composed into methods and into tasks, so it provides some other information. So, but interestingly, for the first IPC, that just that strips part was used, and maybe the only one bit which has been used from ADL was typed representation, so which is at the moment widely supported. So later on, so PDDL 2.1 introduced numeric fluents and durative actions. So it basically somehow add a support for, let's say, consumable resources, like for instance fuel, and some explicit reasoning about time, so that the action takes some time, that some effects can take place at the beginning and some effects can take place after the actual execution finish. So that it basically combines that, let's say, core classical planning part with the scheduling part, because so we need to put the actions not just into the sequence, but also somehow into the time windows in certain way. So, but later on, PDDL 3.1 introduced some trajectory constraints, preferences, and object fluents. So for instance, preferences are some sort of soft goals. That we prefer to, use, let's say, certain airline to go into some place, but it is just a soft goal. So if there is, let's say, another way to get into your destination, so that still the plan is somehow valid, but clearly if we follow the preferences, so the, let's say, plan is, let's say, more valuable if we, let's say, follow the preferences. And with object fluents, so that this is some sort of state variable representation. So which, for instance, we know from SAS+. So that for PDDL, so we can actually specify some functions like state variables. For instance, that we say that, the robot is at certain location. So, and since the state variable is a function, so that it means that, for instance, the robot can be at one location at a time. So it somehow gives us, let's say, more compact and let's say, better representations of certain aspects, because in a predicate way, so we somehow have to just, let's say, list some predicates that are true and that are false. So which means that we have to be extra careful just to make just one predicate saying that some robot is at some location true at time. So, but let's say besides deterministic planning, that there were some other extensions, like for instance PPDDL, which introduced probabilistic action effects, which means that, in classical planning, we know what will happen. Now in probabilistic, that the effects can be achieved with certain probabilities, so that we have, let's say, more options what will happen if we execute some actions. Then recently PDDL Plus introduced some notion of continuous processes and events. So I mean, processes means that there is some sort of continuous activity that somehow changes the environment. Like, I don't know, if you go into the bathroom and turn on the tap so that you can fill the tap, for instance, with water, and this can be described as a process. Event is very similar to action. It also has preconditions and effects like actions, but in this case that events are somehow external to agent. So which means that event can happen, for instance, when the precondition is met, so it somehow happen without agent's will to do this. So while actions are actions of the agent, so that agent can decide whether the agent executes the action. So, and finally, that very recent extension of PDDL introduced some aspects for multi-agent planning, like for instance, what information can be shared by what agent and what actions can be taken by what agents and so on. But besides PDDL, we have other languages. For instance, NDDL and ANML. So both languages were developed by people from NASA because actually they are more, let's say, focused on what we call the timeline planning. So which is very, let's say, close to scheduling, so that timelines, you have some sort of let's say small discrete intervals and you are putting some activities there. And also we have let's say more richer temporal constraints that, for instance, you have I know, like, for instance, they might have battery consumption that's usually not a linear function, so that depends on what activity are you taking and where you are, so that let's say the battery level is changing in a different way. I mean, the only difference between NDDL and ANML is in terms of that ANML is let's say somehow closer to PDDL. Because I mean, NDDL is quite complex. It looks more like Java code. You have more variable representation rather than notions of states and actions. So, which is the case of ANML. So, there are other languages like RDDL. That RDDL became the official language of the probabilistic track of IPC since 2011, mainly thanks to Scott Sanner, who developed that and who is running those probabilistic competitions. The thing is that what is the difference between RDDL and PPDDL is more in that also it can model partial observability, but more specifically that it somehow is efficient when describing Markov decision processes. So, and because a lot of these probabilistic planning techniques are based on those, so that this sort of representation somehow helps the planners. So, and recently that there is a Pycat language, which is some sort of Prolog-like rule-based language. Basically, it's very similar to Prolog. And what is good for this language, that it somehow supports what we call control knowledge. So that, for instance, you might somehow, let's say, put some information into the model, which somehow let's say, advise you which action you should take, if you are in some state and so on. So that basically you have some sort of rules that, in some cases you might be able to enforce specific actions rather than what is, let's say, in PDDL, where whatever action is applicable, so that, it might be applied at time. And also it supports what is called the structured state representation, where basically we might have, let's say, a list of features of some object that, we can somehow handle in a more compact way than in, let's say, classical representations, where we have just a list of predicates and somehow we have to get the information from that. So, And the thing is that if we go back to PDDL, so for instance to PDDL 3.2, which is the latest one, so do we have any planner that support all the features? Well, no, we don't. And if we go really back to 1998, and if we just consider all PDDL 1.2 features, and we specifically ask for axioms and hierarchical actions, so do we have any planner that supports all these? So no, we don't. Right? The thing is that basically we have dozens of classical planners that basically all of them support type strips. A lot of them, especially newer planners, support some ADL features such as conditional effects. So clearly one of the good reasons is because of IPC. So there are some requirements for planners to compete, and I mean usually the requirements are, let's say, very mild, so that if you can handle type strip representation, so you can enter a competition. The only thing in 2014, so that basically we organized and we introduced conditional effects and negative preconditions, so that we at least force planners to deal with, let's say, more expressive aspects of ADL. And also, since classical planning is, let's say, very well studied, so we have dozens of planners and many of them are optimal. So if we want more expressivity, for instance, reasoning with time, then, you know, the number of planners is not that good. So yes, we have some good temporal planners that support durative actions, but also often you need to reason with resources and you need numeric fluence. And here the number of planners you can use and those that support all these features, it dramatically decreases. And moreover, with temporal planning, sometimes you need what is called, let's say, necessary concurrency. So that basically you can't find a sequential plan that will solve the problem, because some actions must be run in parallel, so that there is one well-known domain where you just turn the knob and open the door. So basically when you are turning the knob, you have to open the door, so that you basically need to execute these actions in the same time. So, which means that for planners that are, let's say, based on classical planning and then just, you know, put the reasoning about time after they generate a sequential plan. So those planners won't work with concurrency because they can't find a sequential solution. But if we go further, that for probabilistic planning also we have a couple of that entered the probabilistic track. If we talk about continuous planning, we have, I think, one or two planners that can somehow support PDDL plus features. So, and we may go on. So, the thing is that recently we had a paper on some conference and we got that wonderful comment of one anonymous reviewer. And if I quote, that what he said is, it's almost a law in PDDL planning that for every language feature, one adds to a domain definition the number of planners that can solve or even parse it, and efficiency of those planners falls exponentially. So, I mean, clearly this might be a bit of overstatement, but, you know, if we just go back and to see these numbers, and if we just see the numbers of participants and IPCs, so that basically everything goes like for classical planning. And this is the, let's say, very widely studied area, right? But, you know, if we need some more expressivity, and usually when we deal with real-world applications, so we do need to reason about time, or we need some continuous processes, events, and so on. So that basically we don't have much at the moment we can use. So the thing is that clearly one of the possibility is somehow trying to minimize the number of required features, because actually in most of cases we can relax some constraint or we can do some abstraction, and still it can work reasonably well, because I mean there are some applications. I mean, for instance, that one about genome distance by Patrick Haslum. So it just uses classical planning, and I mean still, you know, you can find some plans that tells you something about how similar two genomes are, or basically what sort of I don't know, operations you need to let's say change one to another. So which you can do with classical planning. But on the other hand, in many cases, so you still need some continuous processes, like for instance what we had in urban traffic control, where you have a flow of vehicles going through the road network and you just, let's say, change the traffic lights. So, and the thing is that the flows of vehicle is some sort of continuous process. So that, you know, we can use that, I think UP Murphy, a continuous planner, but to make it working, we had to develop domain-dependent heuristics. So otherwise, we couldn't get anywhere. So that's the second point. So that not always we can minimize the number of required features and use classical planning. But it is good if we have, let's say, some more expressive planning engines that are somehow efficient, because at the moment that we have a couple of which we can use, but so if we have more and if they are, let's say, more efficient for reasoning with time or with continuous processes, this will definitely help somehow for using planning in real world applications.
Let's move then in a bit more into the knowledge engineering side of planning, and I'm glad that Tiago is here so we can check if I'm saying everything correctly or not. And okay, so what do we mean by knowledge engineering for planning, and actually also for scheduling? It is the process that deals with four main steps, four main aspects: acquisition, formulation, validation, and maintenance of planning domain models. And not only that, actually, because also one aspect that you have to take into consideration when you're speaking about knowledge engineering is the selection and the optimization of appropriate planning machinery to work on it. So the idea is that when you're speaking about knowledge engineering, you want to encode your knowledge in some model, and you are following this step, but on top of that, you want also something which works. So after developing your model, and as we have seen before, the developing of a model is supposed to be independent, but in fact it isn't, from the planners that you are going to use. So for this reason, also on the area of knowledge engineering, you have to deal with the selection and the optimization of planners, basically. And how does this different step come together? That's the overview, basically. So going back to the idea of a real world. So here we need probably to make the distinction between domain and domain model. The domain is the real world application area, is actually the conceptualization of an application area. As we said before, if we are speaking about logistics, the idea of moving things around, the idea of using trucks, depots, boxes, whatever, this is the domain. There is the real world, which is actually, if you go there and if you, I don't know, you can grab, you can't grab a truck, but you can see the truck. That's the real world domain. Then you have the conceptualization, which is your idea of a truck, or the common idea of a truck. And then you have the first step, which is the formulation, which moves from the conceptual idea of a domain to the domain model. And in order to perform the formulation, you need to have in mind also a domain model language in which you can encode the domain model. And once you have this domain model, in a domain model language, it can be PDDL or another language, you moved from the real world to the symbolic world. And on this model which has been generated, firstly you need to validate. So you basically need to check that it complies and that is satisfy the requirements of a domain into the real world. So this step is the validation, which is not only checking that the generated plans are valid, because in that case you are only validating basically against your symbolic model, but you also need to validate against the real world model, which is usually done by involving human experts, which are checking that the generated plans make sense, basically. And then you have a maintenance that is exactly as in software engineering, requirements and the things that users want from your system may change over time. So what you need to do is to maintain your piece of knowledge under the form of domain model, so to make sure that it keeps complying, it keeps to make sense with regards to the real world scenario. And what is not shown in here is the first step, which is the acquisition. And the acquisition is basically the generation of the conceptual domain. So acquisition is usually you sit down with a human domain expert and you try to extract from him the knowledge that you need in order to create the first conceptualization of application area. Usually that sort of document, the way in which you extract the knowledge from an expert, is in a textual form in which you are writing down your understanding of the domain and your understanding of the different requirements. And from that you can then move into PDDL and into the real planning. And yeah, this is basically what has been said in a more formal way. So clearly the domain model that you create is a formal specification of the application domain, and it includes all the elements which are needed for a planner in order to be able to reason upon it, and also for supporting or for exploiting the features of a language that you have selected. And yeah, what I forgot to mention before is that, okay, all of the references are attached at the end of the slides. We will show them at the end, and we will probably make available the slides online so you can check directly. But putting all the names in the slides would become a bit too full of words. And once you have created your domain model, you may want to have to check, or actually you want to check some properties of it. So you want, in order to make sure that the domain model that you generated is actually the domain model that you were looking for, so it makes sense with regards to the real world scenario, you have a number of properties that you must satisfy. And okay, the properties are basically in these ellipses, so you have accuracy, consistency, completeness, adequacy, and operationality. And it is important to note from this slide that each property basically refers to different aspects of the system. So on top you have requirements, which are important basically for all the properties, but the consistency. And then you have the planning engine, but as we said before, you have to take into account for knowledge engineering, but in fact, for the terms of the properties that you use for evaluating a domain models, it is only required by the operationality. And then in the center, you have the knowledge model, which is your domain model. In fact, we didn't mention yet the problem instance, because you can think about it as part of a model. So I think it's not only, but our concept of a distinction between domain model and problem model into two different files, this is mainly due to the use of PDDL. Otherwise, you can think about the domain model as the invariant part of a problem, and then the problem, which is the side of the model that can be changed according to the actual instance that you have to solve. And this part also includes, clearly, the knowledge model language that you have to consider for the knowledge model. But now let's check one after the other these properties. So the first one is the accuracy, which is basically checking that there exists a mapping between the requirements and the model's components. So it basically means you are checking that the domain model that you have generated, regardless of the language, is satisfying all the requirements. So it is accurate with regards to the real world domain, or to the domain in general. And then you have consistency. Now the consistency is the only property which refers to the domain model itself. It doesn't relate to anything else. And it is basically checking, to some extent, the internal coherence of your domain model. So you are saying that your domain model is consistent if some interpretation exists that makes all its assertions true. This is somehow taken, I think, from SAT. But the overall idea is basically that you create your model and then you check if everything works, basically. So you put in there, no, if you're speaking about PDDL, you have some operators, you have some predicates, and then you check, okay, this operator could ever be used. Does it need something else to be used? Or is there any way to reach a specific goal using these operators and these predicates? Am I missing something? Or maybe I didn't consider some predicates which are needed. This is the way in which you check the consistency, which is, as we said, the internal coherency of a domain model. And then you move to completeness, which is, okay, extremely informally, because otherwise the definition was pretty long. You are checking the fact that your domain model is complete with regard to the original domain. So you are checking that if, by using your model, you find a solution, that solution applies also in the real-world domain, and clearly vice versa. So if there is a solution in the real world, you would be able to find it, or at least to represent it, also using the language that you have selected and also using your domain model. Usually, I think, at least according to my experience, it's extremely rare that you find a domain model which is actually complete, because given the trade-off that you have to consider between the expressivity of a language and the performance of a planner, what you tend to do is to try to suggest, let's say, some solution, some shape of a solution through the model that you are generating, and you are ignoring some other possible solution which might be good in the real world, but would be too expensive to encode or to find. And then, okay, another point is the adequacy, in which you are basically checking that the language that you selected for encoding your domain model is expressive enough for addressing the requirements, or that part of the requirements actually. And yeah, it should be noted that you can have a model which is accurate in the sense that you can find the mapping between requirements and model components, but it's not adequate. So let's think, a typical example could be if you are considering a domain model which is important, as the example which Lukáš made before, to have actions which are concurrent, you need to represent them using a temporal PDDL. But for some reason you may have decided to use just plain PDDL or PDDL 1.2, which means that from the point of view of accuracy, your model is still accurate because you have one action for moving the knob and one action for pushing the door. So you are representing all the requirements, but not in a way which is adequate to find a solution which makes sense in the real world. So all the solution, and clearly adequacy, is also related to the completeness from this perspective. And then we have a last point, which is the operationality. So, okay, we have created a domain model in some PDDL language. We have found that it is accurate, it's consistent, to some extent it's completed. The language is adequate for dealing with the requirements or for dealing with the kind of behavior we're thinking about, but there is no planner which can reason upon it. So, to some extent, the domain model we generated is useless, or yeah, it's an artifact, kind of a piece of art. For this reason, one important bit, and which is basically the motivation why knowledge engineering needs also to consider existing planners, is the fact that you need to find a planning engine that can produce solution within an acceptable resource bounds, especially if you're dealing with some application of planning in which your customer or the person or the company for which you are developing a system wants to see some results. And remember that resource does not only mean time. It may mean a RAM or hard drive or bandwidth or anything like that. So it's really a matter of resources. You may have some boundaries in terms of, I don't know, they're running their planning engine on the cloud, and they have only some, let's say, credit which is available, and you have to find a way for generating a solution within that credit limit, which is then set by the cloud system. And yeah. And what is the usual process which is followed for the development of a domain model? So usually, okay, on top, I can't reach it, you have the human modeler, which is thinking about an initial domain model, usually without using any tool. So you have the idea of, okay, I'm thinking about blocks world. Probably I will need to include some predicates which are blocks. I will need some operators for moving things around. You have an initial model. It's not really in a formal language, but you start putting things together. And then the second step is usually the exploitation of tools. So I don't know, you have syntax checker, type and consistency checking, different tools like It's Simple, for instance, which can help you and support in generating a first compilable domain model, where in this sense compilable, since we are not really compiling PDDL, but in this sense compilable means that you have a planner which is able to parse it. So it is parsing, it will not find a solution, but you don't have any syntactic error, or you don't have predicates which are missing and this sort of stuff. After the generation of a compilable domain model, you want to have a runnable domain model. So at that point you exploit a different kind of tools, or the same kind of tool which is able to support all the different actions that you need to perform. So basically in that case you start thinking about the ordering of a goal, you start thinking about, okay, I've got this domain model, I may reformulate something, or it's better to encode this behavior as one operator, two operators, three operators, how many parameters, what should be the exponentiality, how grounded will these operators be, and things like that. And after this process, which is usually the one which takes the longest, because what you're doing is you are dynamically checking the properties of your model. So you find the model, you have a couple of problems or reference, you create it, you run, or you try to run it using a couple of solvers, you have different results, you check, does it make sense, does it not make sense, can I improve a bit the performance? So if the first step basically can be done in, I don't know, few hours, moving from the compilable level to the runnable level can take several days, if not weeks. And then once you have a runnable domain model, which means, okay, I found a way for encoding, I found an encoding which allows the planners to deal with the problem. I've tested it to a few benchmarks and it seems to work pretty well. What I need to do is to prove that it is correct, that it is valid. So basically to check against a part of the properties that we have seen before. So completeness, for instance, accuracy and adequacy. Even for adequacy and consistency has been mainly checked at this level. In here you start thinking about, yeah, does it make sense or not? And you start also using different tools. So you can use random task generators, for instance, for checking all the possibilities that can be covered by your model, or you ask your customer, or you ask the domain expert to provide some more challenging benchmarks or some different kind of scenarios which are not exactly captured by the original benchmarks that you had. And after this task, that again can take quite a lot of time, you have what is called a proven domain model. So it is working, it is operationally okay, and it is valid. And what you just need to do at this point is the maintenance process. So if at some point requirements change, you need to iterate again in order to improve your domain model. And the level, let's say, of a jump depends on the kind of changes which are required. So it might just be okay, we are introducing, I don't know, we are speaking about the logistic example, we have trucks, so we are introducing a new kind of trucks, or we are introducing vans, and we want to treat them in a slightly different way, so they can do the same action of trucks, but we want to know that they are vans. So very likely what you need to do is just to add the predicate, so your jump wouldn't be very long in the backward. So you made a small change, and then you test again that everything is working. Otherwise, if you have some extremely significant changes, you may need even to jump back to the initial domain model idea. And we have spoken about, we have mentioned that exist tools for dealing with knowledge engineering, and okay, this is by no means a complete list, so there are other tools out there, but that can give some sort of overview. So first of all, we divided them into two aspects, into two classes. General framework, we can deal with different steps of a knowledge engineering process, or which can provide some sort of advanced features, and what we have termed here as PDDL editors, which means that they are systems like IDE, basically, for software engineering, which will support you with syntax checkers, with coloring, with brackets collapses and things like that, but will not really help you in all the other steps of a knowledge engineering process. So starting from the shortest class, PDDL editors, we have PDDL Studio, which was introduced 2-3 years ago, I think.
2012.
2000, oh, time flies. And from Czech guys. And then planning.domains, which has been extremely recently introduced by Nir and Chris, which were also the winner of the last international competition on knowledge engineering for planning and scheduling. And this is a website that you can use, and you have the support for editing PDDL and even for generating some common structures, for instance, in terms of elements which are connected and things like that. And it's run on the cloud, so you can also check immediately with a solver if what you have put together makes sense or is compilable or not. And then in terms of frameworks, we have quite a large variety, but the main point, rather than going one by one, I think that the main point is all of them try to provide some support at a higher level for allowing you to design the domain model, and then for generating, if not automatically, but for supporting the generation of the actual formal definition and language. So if you're speaking about, let's say, GPO and it's simple, for instance, what they are exploiting, especially in the case of it's simple, is rather than starting immediately with the PDDL language for encoding your model, you start with a UML language in which, focusing what is done for object-oriented programming, you follow an object-oriented modeling. So you design the objects which need to be represented in your model, you specify their characteristic, you then specify the way in which they can interact, or the way in which they can be modified, and then on the basis of that, part of a PDDL model is generated for you, and part can be modified by yourself. But the important bit is that you also have all the documentation, and you also have all the reasons which led you to that specific PDDL model. And what you can do is also backtrack, and if something is changing, you change the UML and you move forward. And this is something that can be done also in GPO, for instance, which is exploiting a different language. It can't generate PDDL, it doesn't generate PDDL model, right? Or it can generate some sort of PDDL model.
I think it can import.
It can import and then change into its own language.
It can export, but it can't import.
Okay, something like that. And for GPO, what they're exploiting is what has been termed as object-centered language, which is something like UML basically, but more focused on planning. So again, you're using this language for representing, for describing the aspects of your domain model, domain model, and then you can generate the subsequent language which can be exploited by planners. And then we have some other tools which have been developed by NASA, for instance, or by ESA, or by different institutions, trying to support as much as possible all the steps of a knowledge engineering, and usually this means you are abstracting from the PDDL, you are allowing to represent things in a different way, which is easier for the humans and which is easy to document, and then you ground it into PDDL or in a different language. And okay, one question which can be asked at this point is, are these tools really useful? Do we need to use them, or we can just use a text editor as it has been done for the past decades basically? And there was a work, I think from Rabia Gilani, in which the idea was, okay, let's try to find a way for compare different approaches. So let's think that we have one domain model or one specific domain that we want to encode, and let's have 3 different methods for encoding it. We select some themes of the same planning experience, we assign a method to each theme, and we check the final result in some way. So the 3 methods were, okay, we have a PDDL expert which is just using a text editor, which is the common way, I would say, the de facto standard. We have another method which is a user which is exploiting it's simple, and then we have another method in which a PDDL expert or a set of PDDL experts actually are using GPO, which is another tool. And we consider 3 world domains, 3 real world domains. So road accident management, in which the idea was, okay, a road accident happened, so what you need to do is to control the fact that the police is deployed, then the ambulances can go, fire brigades if there are fires, and then tow trucks come and clean the situation. And you have a different position from which they can start, and different places in which the accidents may happen. And then you have machine tool calibration, in which the idea is you have some machinery for performing some operations for a company, and what you want to do is to find a plan which allow you to minimize the calibration time before starting the operations. And then you have urban traffic control, in which the idea was try to find a way for optimizing try to find a way for optimizing the distribution of vehicles in a given region. So the idea being you have vehicle which is coming into your region, and you can imagine that there is a central control that through sat-nav is communicated with the vehicle and saying, okay, you're coming in, this is the situation, so the plan for you is to go through these roads for reaching your goal, because that will reduce your delay time and will distribute the congestion around, so you will not stuck in a queue. Okay, these were the 3 real world, and we consider a number of criteria which were clearly must be related also to some of the properties of the domain models, so, or can be some sort of false friend also. One is operationality, so how efficient are the models which are produced, and that clearly can be checked by using some planners. Or collaboration, so does the tool help team efforts, because we have to consider also that right now we are moving into a direction in which the domains that we want and we are able to handle are more and more complicated and sophisticated. So it's not anymore a one-man work, but you require a team to consider the different aspects and put things together, as in software engineering, as we said before. So then experience. So is the tool indicated for anyone? Does it need some a priori knowledge of planning of a specific language? Efficiency in terms of models which are generated. So how quick can I create a model? Does it support debugging at all? Or does it support the user? So are there manuals available? Are there tutorials? Can I find help somewhere? And basically this is the outcome of this comparison. So in terms of the different aspects which have been considered. So first things which were flagged up is the fact that knowledge engineering tools right now require specific expertise, which can be in planning, or if we're speaking about it simple or GPO, is in the language which is used, or in some different aspects of the tool. So they are not extremely easy to use, and when they are easy to use, they require you to have some knowledge of the specific things that they are exploiting. And then we have no tool right now which can support team working. I know that the guys behind planning.domains, so Chris and Nir, are starting thinking into this direction, but besides that, I'm not aware of anything else in which you can do some teamwork in Zero, or in which the tool is supporting a team rather than a single rider. In terms of maintenance, no tool effectively support the writing of a documentation around the model. So if you're using it simple or GPO, you have the UML or the OCL models, but you don't have any other documentation which can be easily attached or which can be automatically generated, thinking about Java code, for instance, in this case. And another issue is that, again, from the point of view of maintenance, some tools are not able to handle the models which have been modified. So you create a model with a tool, you then create the corresponding PDDL model, you realize there's something is wrong, but if you can quickly change it directly in the PDDL, and at that point you realize that you cannot import it back. So basically you have lost all that part of the work, and you have lost all the support which was provided by the tool. And then in terms of debugging, we have a lack of techniques for debugging, either static, which is basically consistency checking, or dynamic, in which you need to run planners for checking if the model is working or not. Sorry. And then in terms of language which is supported, most of the tools which are available and most of the tools which were tried support a very limited amount of PDDL features. So this can basically be seen as areas in which you have to improve from the point of view of the tools. And for promoting the work from the community on knowledge engineering tools, the international competition knowledge engineering for planning and scheduling, also known as ICAPS, has been introduced. So that was the main aim. As the IPC is focusing on the developing and testing of planning engines, ICAPS is focused on tools for supporting all the different steps of the knowledge engineering process. And yeah, I will not read through that, but this is basically the mission of the ICAPS, which is what you can find on the website. And what's the history of ICAPS? It starts in 2005, and the last one was last year in 2016 in London. And let's say we have two different kind of ICAPS which have been thought about. Like the first one, or the third and the fourth, in which the focus is on tools. So the idea was the competition is about tools. You have to develop your own tool and show its property through demos or through talks or things like that. And then we have what has been done last year, or the second one, I think, in which the focus was on the modeling process. So some scenarios were given, and the idea is, let's check which process you exploit for encoding your knowledge into the domain models, and let's also try to check how the final models are, what are their properties. And let's focus a bit on the last ICAPS, because we know it very well since we were part of the organization. And the idea was that it was a team competition in which the maximum size was for 4 people, and it has 4 different stages. So pre-competition, in which rules and some example scenarios were provided, and then on-site modeling, which was the actual competition. So the teams were all together in a room. They've been given 6 or 8 hours. 8 hours. They've been given 4 different scenarios to encode, which require different level of features from PDDL. And what they have to do is to select, okay, try to encode all of them, but that was impossible in 8 hours. So to select 1 or 2 domains and encode them up to the operational level. So create a PDDL model, some problem examples were provided, try to encode the problems, and try to show that it works with some planners. And we provided also a list of planners for that case. Then there was a demonstration session in which, and that was focused, that allows the teams to describe and to discuss the process from the knowledge engineering perspective that they have followed. The idea being, okay, we know the models, we can check them, we will see then the statistic that we use for checking the models, but since we are interested also in the process side, which is more in the knowledge engineering area, during the demonstration they described the tools, they described the way in which they came up with solution, the different aspects that they have considered, how they distributed the work, and things like that. And the final evaluation was done by a panel of judges that were there during the demonstration and actually asked a lot of questions to the teams, and they were also provided with information about the domain models, so the performance with regard to the planners, and some information about the number of operators, the number of predicates, some features that we can extract from the models. And okay, these are the 4 scenarios which were considered. So one was some sort of Star Trek, which you have a map of a galaxy, and you were required to defend some planets from the attack of a huge, from the attack of some enemy. And what you need to do in order to defend was gathering or collecting some resources in order to build something which can defend yourself. Another example was the roundabout, in which the idea was to represent how vehicles can be distributed through a roundabout, so how they can navigate the roundabout without getting into accidents and collisions. Then the RPG, in which there was a hero which has to move through a labyrinth, which were composed by different rooms, in which there can be monsters or swords for defending from monsters, some constraints about that, but we will see that more in detail later with Lukáš. And then we have a version of a match-free game, in which, okay, the match-free is basically you have your board and you have to swap elements in order to get a free, and if you get a free, the corresponding areas are removed and you are gaining space into the board. And here there were some constraints because some set of frees would result in destroying that part of the board, so making it unusable, and that was some sort of dead end. And the metrics which were used for this evaluation were divided, as I said, in the process and the model. So from a point of view of the process, the judges evaluated the tools which has been used. So if any tool has been developed specifically for the competition, innovation and originality of these tools, or the usefulness and the support provided by the tool. So making sure that they were using the right tools and not just tools for making it sound better. Then an evaluation in terms of a team working, so strategy, collaboration, did put in place any of these things, and then an analysis of the models, where each scenario was assessed singularly, so correctness, readability from the point of view of a human expert, generality, so the ability to deal with small changes in the requirements, and originality. So if there was something which was remarkable or outstanding, or some solution which were very well thought, that were raised up. And also we had a dynamic evaluation of a model by extracting some features information, which I said before, operators, predicates, the number of parameters, which means also the expected grounded of operators and things like that. And also we run some planners on that. And what's the take-home message that we get from the last year ICKEPS? Well, we have a very interesting positive message, which is when we took a look at the PDDL models which were generated, we observed a large variation of the solution which were put in place. And this large variation results also in a significant variation of the planner's performance, which is one of the topics of this tutorial. But this variation was also, let's say, distinguishable or evident on toy-sized instance. So the way in which the model is encoded can make a huge difference also on problems which can be solved in 1 second or so. And that was the plus, and we were very happy with that. But there were some negative sides. So first of all, clearly, the low number of entries compared to the IPC, which basically support what we said before, that the focus in planning seems to be more on the reasoning side rather than on the knowledge engineering side. And then another very worrying point is that most of the teams did not use any tool at all, which was part of the focus, in fact, of the competition. So what we realized is that if you are in a hurry, as they were for that competition, the perceived best approach is just to sit down and start writing in VIM or Emacs or the text editor or window, and keep changing the things and keep using the planners since you arrive to something which is compilable and which works. And another worrying point that we already raised before is the fact that the tools do not support any sort of cooperation. And another important bit, which is highlighted down here, which was not exactly a result of a competition, but some sort of byproduct, is that when we provided the models to the judges, or when we were discussing the model ourselves, we said, okay, but how do we evaluate this? What is the notion of quality? What's the quality for models? And there is no work actually, or I'm not aware of any work which is pointing to a notion of quality for planning, also because it is clearly an extremely hard topic in the sense that quality involves dynamic and static aspects. So when you're speaking about quality, you cannot forget the fact that things are moving. So a model which is very good right now may not be seen as good in a few years, and also a model which right now is not operational, so cannot be sold by anyone, maybe in 2 or 3 years' time you get some planners that deliver extremely good performance of that specific model. So there are different aspects, there are many aspects which are involved into the quality, but at least start working towards this direction could make, I think, a significant change and provide a significant contribution for the knowledge engineering in general and for planning specifically.
So, welcome everyone to the second session of this tutorial. And I mean, the second session will be more about what we call domain knowledge. So, which, I mean, given the definition, so which I found somewhere, so I will just quote it, that domain knowledge is a valid knowledge used to refer to an area of human endeavor, an autonomous computer activity, or other specialized discipline. So, I mean, given the general definition, if we, let's say, consider our automated planning area, so what we can imagine if we talk about domain knowledge. So we need, let's say, some sort of domain-specific knowledge that provides some information that guides planning engines, right? So in other words, this is some sort of, let's say, advisor which says, well, maybe, you know, the plans should like this, or maybe when you apply that action, maybe this is the other action you should apply next, and so on, right? So how do we classify domain knowledge? So clearly we might have, let's say, different use, and there are basically two main categories, and one is planner specific and the second one is planner independent. For planner specific, so you basically have a domain model. It can be, for instance, in PDDL or other language, and then you have some domain knowledge, which might be like control rules, for instance, that is with some sort of linear temporal logic. So, but for planner specific, So you need a specific planner. For instance, a tile planner that somehow can accept the domain model and that domain knowledge and use it in order to provide plan, right? On the other hand, planner independent is basically we don't need any specific planner. So that the advantage is that we can use any, let's say, generic or standard planning engine that, for instance, supports PDDL and that can exploit it. I mean, clearly for the planner specific, so we might have some language like, control rules in linear temporal logic and where we can specify the domain knowledge. If we use that planner independent strategy, so we must be able to encode the domain knowledge into the domain model at the end, because generic planning engine can only accept the domain model and problem specification in some language like PDDL to provide plan. So that for using domain knowledge in planner independent way, so we simply need some translator which will put the knowledge into the domain model. So then basically we have few ways how we can specify domain knowledge. So we can do this by hand. So which means that if we have some expert who know about domain, who know about how plans should look like, so that the expert might specify, for instance, control rules or procedural knowledge, and basically which somehow I will explain later. On the other hand, if the domain expert doesn't know that much about how plans should look like, so that there are some techniques that can generate or learn domain knowledge automatically. For instance, we might have some simple problems in a domain, we generate some plans and then we may examine plans to show that there are some properties that we can exploit. Or also we might do a combination of both. So, I mean, to explain planner specific and planner independent strategy is basically what I already said. So for planner specific, you have domain problem specification. For instance, in PDDL, you specify domain knowledge, then you put it into specific planning engine that will generate plan, right? But for planner independent, you can still specify, let's say, domain model problem specification in PDDL and domain knowledge in some language. But what you have to do is you basically need to take these components and translate it into what we would call enhanced domain model and problem specification. It basically means that you just put the, let's say, the raw domain model and domain knowledge, which might be specified in some language, let's say like procedural domain control knowledge, and you just put it together into what we call enhanced domain model and problem specification. Then we can use some generic planning engine, because we have specification of the model and problem still in PDDL, so preferably with the same or lower expressivity, but still which somehow represents the same model with the knowledge. So then we get what we call enhanced plan. So which might be a plan that not necessarily matches a plan for the original domain model. So because, for instance, I will be talking later about macros that they just somehow assemble some actions together. So and in enhanced plan, so you have just one macro action. So what you have to do to have a plan that is a plan for original domain model, so that you need also let's say some sort of technique that will translate enhanced plan into the plan which is the valid solution of the original domain model. So as you could see, so in this case we somehow decoupling the domain model and domain knowledge. So as Mauro said this morning, so that we also decouple planning engines and planning domain models. So here the question is, why should we distinguish between domain model and domain knowledge if we consider planar independent scenario, where at the end we still need to have some sort of what we call enhanced domain model, because clearly generic planning engine can't accept some, let's say, other information than the domain model and problem specification. So if we go back to ICAPS 2015, so there were a couple of scenarios that the competitors had to model. So I picked the RPG domain, which was one of the simple scenarios, so that we had a couple of teams having 3 or 4 that really generate some models for this domain, so that we got, let's say, some knowledge how experts basically do the coding. So in the RPG domain, so we have a hero that has to go through a dungeon where you have rooms that are connected by corridors. So it's let's say some sort of graph structure, and I mean each room can be empty. There could be a monster or a trap, or there can be sword, right? And also there is one property that basically the hero can visit a room at most once. Then for some magic reason, when the hero left the room is destroyed, so that the hero can't go back. So, and basically what the hero can do, so clearly he can move to adjacent room that has not yet been visited, so it's not yet destroyed. So the hero can pick up a sword. So if the sword is in the current room, then if the hero carries sword, so he can somehow destroy it, so that the sword is lost forever. The thing is that there is another action where hero can disarm a trap. So clearly the trap must be in the current room, but the hero has to be empty-handed. So the hero can't carry the sword in order to disarm the trap. So the thing is that clearly we have monsters and traps, so that they are somehow dangerous to the hero. So the thing is that what happens is that the hero can die if the hero is empty-handed, so he has no sword, and the hero is in the same room as some monster, so the monster will kill the hero. Or if the hero goes to a room with a trap, but if the hero performs any other action other than disarm trap, so the trap will explode and will kill the hero. So if we just let's say focus on the move action in this domain, so that what we can see is that basically the hero dies if basically the hero moves to a room with a monster without a sword. So if the hero is empty-handed, so I mean technically the hero can move to a room with monster, but then the monster will kill him. Or if the hero is already in a room with a trap and try to move away before disarming it. So the trap is active, and since according to specification the trap will explode if the hero performs any other action than disarm trap action. So if we have those requirements, then I mean let's say one would expect somehow that for the model, so for instance you will use some sort of conditional effect, so that I mean if you arrive to a room and there is a monster, you are empty-handed, you will die. Or if you are moving away and there is active trap, you will die. So but what basically all the competitors did, that they basically define 2 different move actions. One is if you have sword and perform a move action, so basically you can enter any room without trap, so that you can enter empty room or a room with monster if you have sword. If you are without sword, then you know, the hero means that the hero is empty-handed, and the hero can enter rooms without monsters. So which means that the hero can enter empty rooms or rooms with traps. So, I mean, in other words, so what competitors did is somehow to avoid hero's death, because this was not really explicitly modeled. So if we go back, that basically according to specification, basically if we have this move action, or if we go even into the previous slide, so that basically you know, there are not restrictions where to go. Basically, we can go to adjacent room which has not yet been visited, so it's not destroyed. So it doesn't say anything about that we can move to a room with a monster without sword and so on. So on the other hand, clearly there are some consequences if we do this, right? So if we are empty-handed and the hero moves to a room with a monster, so the monster will kill the hero, and then the hero, if the hero is dead, so the hero can't perform any action and will never achieve his or her goal, right? So, and basically what the competitors did was just to say, well, there is no reason for a hero, if the hero is empty-handed, to, let's say, enter room. Well, if the hero is empty-handed here, to enter room, so with monsters. So because clearly if the hero does this, so the hero will die, and similarly for traps, right? So that's basically what they did, is that they somehow avoid what we call dead-end states. So states from there the goal can't be achieved. So I mean, in case of hero's death, it is literally dead-end state, right? And I mean, clearly, yes, avoiding hero's death is a good thing, right? Because clearly, you know, we want the hero to achieve a goal, to go into some goal room and escape the dungeon, right? So that, you know, he can't die during the process. So, and so this is basically what those experts took into the account when they created the model. So, however, the thing is that those models don't really fully correspond with the specification. And there might be a good question, what can happen if, I mean, something changes in the specification, or you might have certain problem where you really want to kill the hero and that model will not allow it, right? So that's, there are some, let's say, discrepancies between the specification and between the models, right? So what was the observation was that basically, you know, those competitors were experts in planning, and they really knew how planning engines work, right? So what they were doing somehow, if we generalize, that they were encoding the models in what we would say in a planner-friendly way, right? Because if you avoid what we call dead-end states, it's basically if you have the possibility to arrive in a dead-end state for a planner, so it might mean that the planner needs more time for searching for the plan. So which means that clearly it is a good thing, so to somehow put some, let's say, additional constraints into the model that will somehow avoid the situation where, let's say, the hero dies, right? On the other hand, the problem is that you know, the models are not, I would say, even accurate or complete according to definition, because they don't really correspond with the requirements, because the actions are somehow described in a different way. And also this might be in some cases, well, this is, let's say, a toy problem, but I mean in more complicated cases, somehow expert models might be difficult to understand by non-experts. So because actually the actions are described in a different way than the requirements set, right? And that's the reason why we should somehow separate the what we call raw domain models, that those raw domain models that are really accurate, complete, and they really correspond with the requirements, and what we call domain knowledge, which I mean in our case is somehow preventing hero's death, right? So, and well, now we somehow presented, let's say, a general case how we can separate and what is domain knowledge. But I mean clearly, you know, for planner independent scenarios, so that you know, we need to come, let's say, with some types of domain knowledge that can be used, let's say, for, let's say, a large set of different domain models. So one of the best known type of domain knowledge is macro operators, right? The thing is that basically what we can do, we have some ordinary planning operators or actions, and we can somehow assemble them together so that we represent a sequence of ordinary operators as a one macro operator that still can be encoded in the same way as, let's say, the ordinary operator. Still you have preconditions and effects. And yeah, clearly, you know, if you apply just one macro, then you get the same result as applying the sequence of ordinary operators. So, and I mean, why this can be useful? Because I mean, macros often represent frequent sequences of ordinary operators in plants, so that it might be better just to apply one macro action or one macro operator rather than looking for some, let's say, sequence of ordinary operators. And I mean, we have, I mean, a lot of works, I mean, starting in, I think, early 80s with macro problem solver. So, and you know, to be, let's say, to show some example that, you know, we can imagine some simple box word domain where we are just, we might define these two operators, unstack and put down. So what unstack does is that it unstacks a block from some stack, and the robotic hand is holding the block after that. Then putting it down means that when a block is held by a robotic hand, the block is put down on the table, right? And I mean, if you want to somehow assemble this sequence of ordinary operators into some macro operator, what you actually do is that you move that block from a stack to the table just directly without having that intermediate state where you hold that block. So, and basically this is how we can encode it, right? That this is the PDDL encoding for unstack and put down, and this is the resulting macro operator unstack put down that basically put these sequence of operators together. And I mean, clearly, as you can see, that basically this has a similar structure, that still you have preconditions and effects. So that's why macro operators are so widely studied, right? And we have plenty of approaches. For instance, macroFF that defines some rules where we generate macros, which I mean means that, for instance, I mean, they need to somehow share some objects in between, and they have to be what we call some sort of locality rule, where we use what we call abstract components, which means that a certain class of objects are somehow related to each other, and so on. And basically, what that approach does is that it generates some macro operators, then run some training phase, and just select the top K frequent macros in training plans. So Wizard is exploiting genetic programming approach, which basically means that it somehow tries a lot of possibilities to pick up some good macros from training plans, and then somehow test them on a given planner. So the thing is that for macroFF or for other approaches, that these learned macros are, let's say, the same for all the planners, while I mean Wizard is considering the performance of that given planner that is used to learn macros, but clearly this is still planner independent strategy, because you can learn macros for basically any planner that supports, I think, type strips PDDL. So then another work which was considering somehow what we called dependencies between actions in plants. So which means that, I mean, in consequences that just we don't look just for, let's say, direct sequences of actions in plants, but sometimes we know that sometimes these sequences are interleaved by actions that are independent, that can be somehow moved before or after the subsequence of interest, and we somehow don't have to consider these actions. Right? And I mean, moreover, this approach somehow supports removing original operators from the domain models if the original operators or the instances of original operators are replaced by macro operators in training plants. And one of the recent work covers somehow uses problem decomposition in a way that the approach somehow achieves each goal separately. Then basically these plans that achieve single goals are considered as macros and put back into the domain model and used for solving the problem. So there are clearly more approaches, right, for macros, but we just selected some interesting ones. The thing is that, I mean, in general, macro operators are kind of shortcuts in a state space. So which, I mean, we can somehow jump from one state to another in one step rather than taking several steps. So that it's, in other words, it means that, you know, the plants considering macros can be or are shorter. So which means that we don't have to go that deep when we search for a plan. So good thing is that macros can quite easily generalize. So I mean, as I showed in that Bloxworth example, that, you know, if we use, let's say, classical representation where we use parameterized actions or operators, so we can do the same for macros. So clearly in the learning process we have let's say some specific instances of macros, but we might say, well, you know, if we unstacking a block and putting it down, so that, you know, we can generalize it. We can just do for any block. So that's what we can do. And moreover, if we add macros into the domain model, we are just, let's say, adding some transition in state transition systems that basically are somehow still covered by other transitions. So in other words, we are not, let's say, losing what we call soundness or completeness of the model. So soundness means that the plants, if we somehow unfold macros, if we replace macro operators by the sequence of original operators, so we will get the solution for the original problem. And completeness means that adding macros into the domain model will not theoretically affect solvability of the problem. So which means that the problem with macro is solvable as well as that if and only if the original model is solvable. On the other hand, the problem with macros is that they can have a lot of instances because they cover sequences of operators, and which usually means they need, say, more parameters, and you need to instantiate those parameters, and you have simply much more combinations. So which means, in other words, that branching factor, which means let's say how many actions are applicable in a certain state, is or can be much higher. And clearly, since we have a lot of instances, and what planners do is just initially they do grounding, which means just to provide every reachable instance of basically every action in the domain model. So which in the case of macros means that memory requirements are usually considerably higher. So, I mean, the interesting aspect is that we have some works that are somehow like anti-macro approaches, I would say. One work is, I think, from Patrick Hasslum and someone else from, I think, 2001, and they basically remove what they call the redundant actions. And basically, according to definition, the redundant action is an action whose effects can be achieved by applying sequences of actions, right? So which actually means that this approach is somehow trying to identify what we called macro actions and remove them. So, and I mean, in some cases it can work if, let's say, that macro is not useful. And also there is another recent work that somehow splits is operators or action schema in terms of that we have some, let's say, complex action or planning operator, and it is somehow decomposed to simpler ones. So that, I mean, let's say, if we consider unstack put down as a complex action, so that this approach will basically split it into unstack and put down. So, another type of domain knowledge are entanglements. Those are relations between planning operators and predicates, and the main aim of these relations is to reduce branching factor. So, I mean, in other words, we are somehow looking for pruning of some, let's say, unpromising alternatives in the search space. So, the thing is that one of the good property is that entanglements also can generalize quite well, similarly to macros, so that they are often domain specific rather than problem specific. And also we can encode entanglements into the domain model and problem specification, so that we can keep that, let's say, planner independent type of domain knowledge. And similarly to macros, so we can learn entanglements from some what we call training plans that are solutions plans of simple planning problem in a given class, usually when we have some domain model and some problems in there. So we have two types of entanglements. We have outer entanglements that are relations between planning operators and initial and goal predicates. So the thing is that what they basically do is they just directly reduce the number of possible instances of planning operators. And we have two subtypes of outer entanglements. The first is what we call entanglement by init, which somehow allows instances of a given operator that only require instances of a given predicate that are present in the initial state. And similarly to entanglement by goal, that allows only instances of a given operator that achieve instances of a given predicate that are, let's say, required as a goal. So that, I mean, in this example, again in blocks world, so that, you know, we can see two operators, unstack and stack. And since the common situation for blocks world is that, you know, we have some, let's say, initial situation where we have some stacks of blocks, and in the goal situation we just would like to build a different stacks of blocks. So what somehow we can see is that, you know, we can find the relation entanglement I init between operator unstack and predicate on. So what does this mean in this case? So with this initial state that we have block C on B and block B on A. So that entanglement basically says that what we can do with unstack is only to unstack C from B and B from A. And that's it. So we don't care about any other, let's say, combination of blocks, that we are just unstacking blocks from their initial position. And similarly for stacking. So we can see that the operator stack is entangled by predicate on, and if this is some goal situation we would like to achieve, that A is on B and B is on C, so we just need only those instances of stack operators, so we can stack A on B and B on C, and we don't have to care about the other instances. So, and I mean, exactly in this case we can quite considerably reduce the number of instances, because the number of those instances is, I mean, in general is quadratic, because you somehow consider every combination of blocks. But in this case, since you know, you can have a block only on another block initially, and or only other block in, say, the goal state, so that the number of instances of these actions, when we consider these outer entanglements, is linear. So, and since we won't like to, let's say, encode the entanglements, so for outer entanglements it is quite easy, because we know that this operator is, let's say, entangled by init with predicate on, so we somehow create a static twin of predicate on, and somehow we just adjust the initial state by putting instances of static on that are the same as instances of on in the initial state. So I mean, in this case it will be static on CB and static on BA, and since this is static predicate, so which is in the precondition, so which somehow just restrict the, you know, the number of instances that the unstack operator can have. So let's move to inner entanglements. They are somehow slightly more complicated, and they somehow capture exclusivity of what we call predicate requirement and achievement between pairs of planning operators. So we have two subtypes. One is entanglement by preceding, where basically a given predicate for a given operator is exclusively achieved by another operator. So which basically means that entanglement by preceding says that a certain operator wants some predicate exclusively from another operator, so, and not from any other operator, right? And similarly, entanglement by succeeding. So we have an operator that achieves a given predicate exclusively for another operator. So which means that basically if that operator is achieving a predicate, it's always for that given operator and not for someone else. So I mean, we can see it on this example. So for instance, we might have a predicate holding. It basically captures that relation that block is held by a robotic hand, and we have basically two operators that can achieve this predicate, right? That in this case it's unstack and pickup. So then if we want to use that holding predicate by operator put down, so we get here, and the thing is that in this case, that I mean, the nature of exclusivity is I mean, somehow straightforward, because here you just see if you pick up a block and put it down, you basically are in the same state as before, so it really doesn't make much sense to do this. So this means that basically if we want to apply an operator put down, then the precondition, which means that you know, the robotic hand has to hold some block, must be achieved by operator unstack. Similarly, we might have two operators that require predicate holding. So these are stack and put down. So the thing is that if we achieve that predicate by operator pickup, so and then apply operator put down, we are again in the same state as before, which is meaningless. So which means that if we achieve that predicate holding by operator pickup, so then this predicate should be somehow used by operator stack, so that we can go to a different state. But I mean, this is again quite a toy example, so that I mean, in general, we can capture these relations, but let's say the nature is let's say not that easy to find. So because anyway, just if we look at the encoding of inner entanglement, so I mean in this case is entanglement by succeeding, and the thing is that it is, let's say, not that easy as in the outer entanglement case, because what we need to do, we need to introduce some supplementary predicates that again are some sort of twins of, let's say, the predicate which is in the relation, in this case holding, and those predicates are used basically to somehow lock undesirable operator sequences. So the thing is that what happens when we apply action pickup. So we somehow achieve that predicate holding, but we somehow, let's say, delete this supplementary predicate that is required by action put down, which means that if this happens, so that put down will become inapplicable, so that the only action that can be applied is stack, right? And then when you apply this, so that you somehow follow the relation of entanglement, so that you can let's say put the predicate back. So because I mean at some point you might let's say use a different sequence where using put down will be legal. So the thing is that clearly pruning of unpromising alternatives in the state space is beneficial, and also especially in the outer entanglements case, that also memory requirements are lower, so which is good. And again, similar to macros, we can easily learn entanglement, so just we can go through training plans and we can observe if those relation applies. And I mean, moreover, what is beneficial is that let's say we don't have to know about the nature why these inner entanglements hold, but we simply say, well, if we can observe, and then we can somehow test for in other problems to see whether somehow they hold, and so if it happens, so that we can use it, because clearly the, let's say, problem is that we are pruning something, and it depends that we have to learn correct entanglements. Clearly, if we select the not very representative set of training problems that might be somehow specific and over-constrained, we might identify some entanglements that are specific just to that set, and it doesn't generalize. So, which means that if we enforce incorrect entanglements for problems, so we somehow over-prune the space in a way that we will not find any plan. And similarly to macros, so we might have what is called utility problem, that sometimes, let's say, the relation, especially it is the case in inner entanglements, that they might not be that efficient for a given planner. So, and to show some results of, let's say, macros and entanglement. So we, I don't know, a couple of years ago, I think 2013, so we developed a planner called ASAP that basically learns the most promising couple encoding and planner. So which means that we have encoding, we have original domain model, we consider macro operators, outer inner entanglements, and both outer inner entanglements together, and then we considered a couple of state-of-the-art planners like FF Satplan, MP, Llama LPG, SGPlan, and Pro. So, I mean, we basically, let's say, aimed for either speed and quality. So for speed, it means that to generate any plan as fast as possible, and with quality, we were given, like in IPC, 30 minutes to generate as best plan as possible. And basically, here are the best couples we learned. And interestingly, there are a lot of differences, not only planners but also encodings. that come around. So that, I mean, clearly it depends on encoding and planner, and it makes some sort of, let's say, variation. So that's why we need that sort of types of domain knowledge to somehow consider, because let's say, in a certain domain and in a certain planner, for instance, this combination works well. And clearly we somehow compared against the, let's say, best single solver, which means that just the best planner for the original model, and clearly in most cases that we were far better. And also more interestingly, that for instance in Bloxworth and Deepos, that the probe planner, or the, I think, 2011 version, right? So was, let's say, the best single solver for the original problem, but including both or outer entanglements, that FF became the best planner. And I mean, for instance, here given the results, so that it clearly outperformed. I mean, in terms of quality, the difference is not that huge, but still, I mean, in general, we can improve quite well. So, and we were thinking about, okay, so macros are, let's say, good for, let's say, putting or providing shortcuts in the search space, but they suffer with increasing branching factor and too many instances. While outer entanglements are basically going against the branching factor. On the other hand, if we apply outer entanglements on original operators and we are not sure about that we selected good training problems for learning, so that just to, let's say, avoid incompleteness, we say, well, we just apply outer entanglement just on macro. Because if we somehow over prune instances of macro operators, it doesn't matter, because still we have these original operators, then we can use instead. And moreover, since outer entanglements somehow say that a certain operator, if entangled by init, should be used somehow at the beginning, while that one which is entangled by goal should be somehow used at the end because it achieves a goal. So that we can use outer entanglements as some sort of heuristic. And we got pretty nice results. So we clearly compare with the original model and with macros learned by Wizard. And moreover, Wizard had advantage that it somehow learns more suitable macros for each planners, while in our case it was general. So, and I mean, clearly, so our results are quite good, and we really outperform both original and Wizard. There is one small exception, and this is the LPG planner, where the original encoding was better, and very likely the problem is that for LPG, if we somehow even slightly increase branching factor, so the planner doesn't really like it. So, to summarize that learning planner independent domain knowledge. So that the thing is that knowledge like macros and entanglements, this is quite easy to learn. So we usually need just a couple of simple training problem instances, and which are usually very easy to solve. And we can observe the, let's say, required structure either for learning macros or entanglements. And moreover, we also don't need any, let's say, explicit knowledge from an engineer. So we just do some observations from training plans, and basically then we exploit that observation later. So, and again, the good thing is that macros and entanglements, they generalize quite well. So as we have shown in the results, so that's basically if we learn from a very simple training problem instances and apply it for, let's say, more complex problem instances in the same domain model, so that the performance of the planning engines can often significantly improve, right? That means that it is quite good. On the other hand, as we observed in the case of the ASA planner or even for MAM, that clearly there are different impacts per domain and planner. That sometimes that some domain knowledge really helps the planner and is really useful in a given domain, and in some cases it is not that much. So there is another possibility how to specify domain knowledge. So if we do this, let's say manually, then often we can, let's say, get much more efficient models or enhanced models, right? Clearly we need some sort of expertise, because if we manually encode that domain knowledge, the problem is that we need to know, for instance, about how the plans should look like, or I don't know if there are some, let's say, other relations between actions in the model. So mostly this sort of domain knowledge, like procedural knowledge or transition-based control knowledge, that you need to know how the plans should look like. So that, in other words, you are somehow encoding some, let's say domain-specific features or domain-specific algorithm into a planner-independent scenario. So, with regards to procedural domain control knowledge, that's basically based on the procedural programming paradigm. So that's, if you imagine a programming language like C, but much simpler, so that this is basically how we can define procedural domain control knowledge. The thing is that, for instance, in contrast to like control rules, that this domain control knowledge is action-centric. So it basically says how, let's say, actions should be ordered in plans, right? So which is what we say here. And also, the advantage of that procedural domain control knowledge is that it can be encoded in planning domain models. So, and to see some examples of procedural domain control knowledge is, for instance, if we have this expression which says that, while B is not clear, which means like some block B, then we choose any other block B and put it on the table. So it basically says that we would like to somehow release block capital B from the stack. So and we will just repeat let's say the put on the table operator, which somehow puts blocks that are somehow stuck on top of capital B on the table until B become clear. Or, for instance, if we have this expression, we can just say, well, we perform any sequence of actions until some A, like package A, is loaded in track. So, which means that in this case, we somehow don't know exactly what we should do, but we would like to, let's say, achieve this sort of sub-goal. Or, for instance, if we have some alternative, then we can load some package C either to plane or to track, and then we can fly the plane or drive the track, and at the end the package will arrive to LA. So another type of domain control knowledge is what we call transition-based domain control knowledge, and this is inspired by finite state automata, and again is action-centric. So the slight difference between procedural and this knowledge is that basically what we do is that we define some sort of grammar, right? And we define the grammar of solution plans. So that's again, so we somehow say how solution plans should look like. I would say that the transition-based domain control knowledge is, because it's what we would say more schematical, that's easier to understand by non-experts in planning, because this basically follows some observation with, let's say, domain experts but not planning experts, that they prefer some sort of diagram that are similar to finite state automata. And similarly, to procedural domain control knowledge, also transition-based domain control knowledge can be encoded in planning domain models. So here if we can see the example, so that again this is some sort of toy example from logistics domain, that basically we can see that if we have an empty truck that somehow can carry at most one package, so we should move it only to location where some package is waiting to be delivered, so which is basically captured by this condition. And if we can load some package, so that we can move to that state, and clearly we load only packages that has to be delivered somewhere else. So we are not loading packages that are already in their destinations. And when we load a package, so that we have to drive basically to the, let's say, package destination or package goal location, which means moving here, and then we unload the package there. So I mean, in other words, that basically this sort of structure says something about how the plan should look like, because I mean the raw domain model, it just specified that the truck can drive between locations, then the truck can load, well, at most was one package, so that it can load a package if the truck is empty, and if the truck is carrying some package, it can unload it. So, but with those, let's say with that other knowledge, where you just put some more constraints on that scenario, that you just somehow specify the grammar or the shape of the plans. So because clearly for empty truck, so that it should move only to place where it can do something. So for instance, where it can grab a package which can be delivered somewhere, and if it already has package, so it has to deliver it before doing anything else, because there is, let's say, no capacity for truck. So and right, and for transitional domain control knowledge, so that one of the benefit is that in some, I would say, simpler domains or with simpler domain models, so if we, let's say, apply this transition-based domain control knowledge well, so we, I would say, somehow we are determining the planning process. And it was the most apparent in domains like barman and city car, where basically the thing is that we can somehow achieve goals one by one. On the other hand, it is not, let's say, that simple, because still there are some variations, because I mean for barman, so that you might need to prepare cocktail, and sometimes you might reuse a glass with the same ingredients and so on. But I mean in general, basically every planner was able to solve the enhanced domain model with the domain control knowledge. And with city car, where basically it is a new domain from IPC 14, then you have to navigate cars through the grid, and moreover you have to build the roads in the grid. And you have some limits that, I don't know, you might build only, 6 roads at most. And well, the problem is that if you, for instance, start to considering, let's say, and put all the cars into the network, you are not able to distribute it, because you don't have enough road to navigate them. But I mean, if we specify that knowledge where we can basically navigate cars one by one from their initial to the goal destination, so that basically we were able to solve every problem in the set. So except for YAS Planner, because it didn't support conditional effects, that was a requirement for this domain. But for the original setting, at most we solved 9. So which means that, if let's say domain control knowledge is used right, so then the performance of the planning engines in general can be improved a lot. So I mean, if we somehow summarize that domain knowledge part, that for, let's say, simple kind of domain knowledge, such as macro or entanglement, you know, they are, as I said, they are easy to learn, and we don't need expertise. So we just observe some properties in what we call training plans. On the other hand, it might not be that efficient in general. On the other hand, if we use these what I would call the sophisticated kinds of domain knowledge, so that, I mean, in some case we can really make the planning process, I would say, even deterministic, because to be honest, a lot of models are quite easy in terms of complexity, but since let's say planners are domain independent, they might not deal well with the raw specification. But if we specify some additional domain knowledge or domain control knowledge, which will provide a good information about the shape of the plans, so sometimes we can really improve the performance quite a lot. On the other hand, well, I mean, it is not easy to, let's say, automatically learn. There was some paper, I think in last ICKEPS, that they were able to learn procedural domain control knowledge to some extent. On the other hand, there are still some problems, because I think this was limited by number of lines of that code that the procedure can have. So that's why, you know, this is quite difficult to learn. So, and if you have to specify it manually, so that clearly you need some knowledge about the domain or about the shape of the plans. So on the other hand, if you, let's say, if you have it, so then, you know, you can provide it to the planners, and the planning process can be, I would say, considerably improved.
So we have seen some, let's say, sophisticated way for learning domain control knowledge, but there are other ways which are fairly simple, I would say, quite trivial, but which can still lead to some significant performance improvement. And this is the case of what we call, or what has been called actually, domain model configuration. So the idea was, some results were presented in ICKEPS 2015, but it was something which was well known, or at least suspected, by a good 10-15 years. So the idea was the order in which you list the elements within a domain model, in this case focusing only on PDDL, can affect the performance. So specifically, the focus was given to the way in which domain predicates are declared, or the operators. Which operator do you list first in the domain model, and within the operators, what is the order of precondition and postconditions. And we performed this analysis by exploiting some algorithm configuration techniques. So we use an algorithm configurator, which was called SMAC at that point, which is still called SMAC, which is based on, it's a model-based algorithm configuration technique. So what it does, and it's usually applied to algorithms, is you provide an algorithm with a number of parameters, it tests different configuration of this algorithm, it generates an internal model of the performance, of the expected performance, and then given this internal model, it investigates the area of the configuration search space which look more promising. And we use it for configuring domain models for a given planner. And how does it work? Basically, the notion of parameter in this case was basically corresponding to the position of the element in the domain model. So let's say that we have an operator which is composed by 3 preconditions and 4 effects. That will result in having 7 parameters which can be configured by SMAC, so 3 for the precondition and 4 for the postcondition, and each of the parameters has a value which is in the space between 0 and 1. And the higher the value, the higher the value that is given to this parameter, the latest the element is listed inside the domain model or otherwise said, the smaller the value, the earlier you are listing the element. So let's say that, going back to our example in which you have 3 preconditions and 4 effects, P1, P2, and P3 correspond to the precondition, so you can assign one value each between the 0, 1 range. So let's say that, for instance, you have this value which will result in a domain model in which the preconditions are listed in this order, where you have precondition 2, which corresponds to parameter 2, which is listed first because of a very small value, then precondition 1, and then precondition 3. And this sort of approach can be extended for considering all the preconditions and all the effects of all the operators, and the sequence of operators, and the sequence of the predicates. It results in a pretty large configuration space, but that can be managed by SMAC, which was also used for doing some algorithm configuration on Cplex or on other quite complex systems. And we observed quite a number of interesting results. So at first, intuitively you might think that, and we were thinking that, we wouldn't have observed some extremely significant differences, also because there are some planners which are reordering the actions themselves. But the first thing that we observe is that if you are configuring a domain model for a specific planner, so with a specific planner in mind, basically you are passing to SMAC the information about the performance of a planner of a configured model, you can statistically significantly improve the performance. And as has been observed also by Lukáš before, the way in which the planners are affected by the domain control knowledge, or in this case by the configuration of a domain model, they are not all affected in the same way. So you have some differences, which means that the relative performance of planners are different, which basically means that if you are running a competition or if you are running a benchmark, the domain model configuration that you are using for comparing the planners may result in a different outcome from the competition. And another important or interesting point that we were asking ourselves is, since we can find a domain model configuration which improves the performance of a specific planner, but this requires some time, because for running the algorithm configuration techniques you need 5 days, 5 CPU time days for creating the configuration, and then you can use it. But since we have extracted a few of them, considering these sort of planners, is there a configuration that improves in general the performance of all the planners? And the answer was yes, which basically means that despite the fact that planners, or reasoning side of a planners is different, the wrappers are different, the parsers are different, there are some components, there are some aspects which remains the same for all of them, and which can basically support the planning process. And okay, in that case, what we were doing is some sort of analysis for identifying, okay, we observed that the main element which can have an impact on the performance is the order in which you put the operators, in which you list the operators in your domain models. But is that a general characteristic of each operator, is an absolute characteristic, or there are some relations between the operators? And we observed, this is a graph that can be generated using FANOVA, which is a tool that comes basically with SMAC. It has been developed by University of Freiburg, which puts together the value that you can give to the parameter. So in this case from 1 to 0, which is not shown, and this parameter corresponds to 2 operators, drop and load, in the depots domain. And then you can see how the performance of the planners are affected by the corresponding value. So in these terms, in this graph, the performance are shown in terms of par 10, which is the penalized average runtime, which basically means you are doing the average of runtime by considering if the problem is being solved, the actual runtime, otherwise 10 times the cutoff time if the problem was not solved. So you are basically putting together in a single metric runtime and coverage. So the higher the par 10, the worse the coverage and the worse the performance, the lower it is, the better it is. And we can observe that there is a a clear area, which is down here, in which the performance are better, and which basically correspond to the area in which the drop operator has a very high values, which means is listed later, and the load operator has a low values for the parameter, so it is listed before, which basically indicates that there is some causality between these two operators and between the way in which they are listed. And clearly, one aspect that we observe is that, yes, you can improve the performance by reconfiguring the domain model, but you can also decrease the performance. So it's not a matter of, okay, I have an original model, I can just randomly reorder the elements and I will get very great performance. No, you can decrease the performance. And as general observations that we were able to synthesize from the analysis, we observe that operators are the aspect, as I said before, which have the strongest impact on the performance, and they should be listed according to two aspects. One is directionality, which means in domains in which there is a clear sequence, there is a clear way in which the action should be used. So if you're speaking about the depots domain, you have to load something before unloading it, and usually you have to load something on a truck, driving, and then unloading. This directionality should be followed also in the domain model. Or in domains in which the directionality is not observable, it's better to follow the frequency. So operators which are expected to be used the most should be listed early in the model. And similarly, the precondition which is most likely to be unsatisfied should be listed earlier. That's probably because in that way it's easier and faster to check if you are failing in some precondition or not. And similarly, the main effects, so if you have an operator, usually you have a number of effects, but there are one or two effects which are the reason why you are using it, and the other are basically side effects. So those main effects should be listed earlier, again probably for the same reasons of a precondition. And okay, and predicates should be declared following their frequency as preconditions. And that basically concludes this part on domain knowledge, domain control knowledge. So we have covered different aspects which include complex reformulation or easier way for reformulating, like the domain model configuration. Let's check something which is a bit on the boundaries of the focus of the talk of today. So one thing is we have seen that domain model encoding, so the process of the formulation step of the knowledge engineering, is extremely challenging for humans. And so the question is, also on the basis of the machine learning techniques that we have, or on the basis of experience that we gain as encoder, can we do it automatically? So can we provide some sort of raw data or information to a system which will then come up with a complete domain model? And the answer is yes. There have been a lot of studies in this direction and in this area, and clearly there is a significant variety in terms of different perspectives that are considered by domain model acquisition systems. So clearly one main question mark is about the kind and the amount of input that you require from the system. What is the model which is provided as output? Is it a complete model? Is it incomplete? Is only the operation schema? The languages which are supported both for input and output, and the ability of this system to deal with noise. These are the main aspects that you should keep in mind when you're dealing with automatic domain model acquisition. And here we have a list, again, of tools, and again, by no means complete. It's also probably there are, or not probably, I'm sure that there are some new tools, and a couple of those are also presented in these ICAPS this year, but we were not able to find the papers to put them into the list by now. And so we have this number of systems. And you can basically check against the dimension that we were mentioning before. So we can see that we have different ways in which the input can be provided. So for instance, LOCOM requires only plant traces and is able to return as output a complete domain model in PDDL, but it is not able to handle noise, so it is believed that the plant traces are valid. While there are other systems like, I don't know, OpMaker, which requires, also OpMaker doesn't deal with noise. Let's say Aman. The names were provided in the work 24, which I think again is from Rabia Gilani. And since some of the systems didn't have a clear name, the acronym was generated by considering the title of the papers. And for Aman, for instance, we can see that the input which is required, it accepts noisy plants. Again, it is able to deal and to generate a complete domain model, though in strips and not in PDDL. But the main point is that it can address noise. And other things which are not shown in this table is basically that there exists a range of tools which have been built on top of LOCOM, such as LOP or ASCOL, which are able to deal with some numerical aspects of planning, or which can increase the quality of a domain model which is generated by LOCOM. And another, let's say, direction in which we are start working right now, or we as a community, not we as people or researchers, is the fact that, okay, we can encode something manually, so we have an expert which is dealing with that, or we can exploit some learning approaches, but maybe for learning approaches you need a lot of data to be provided as training. And what if we don't have data, but we have a lot of people which can work on that? So basically the crowd which can work on that, thinking about Amazon TAC or something like that, in which you can provide a very small task to people and they get paid for doing the job. So can we exploit this sort of approach also for the domain model acquisition? And that was addressed in what was called CAMA, crowdsourced action model acquisition. So the idea being that you have a domain in mind, but you don't know exactly, you don't have a great expertise of the area. So you have a general idea of the operators which you can be in place, but you don't know exactly which precondition of effects. And this is exactly where the crowd help. So the set of operators, the name and the parameters were provided, and then annotators were in charge of accepting or rejecting potential precondition and postcondition. And also the annotators were provided with plant traces if they were available. And what came up is clearly that according to the annotator, according to the set of annotators, you can have very different suggestions for the operator. So what was done at that point was using a max-sat approach for trying to merge together all the knowledge which were covered and collected by the different annotators. And the results in this direction are extremely encouraging. So this seems to be a direction which can be pursued for having this sort of crowdsourced domain model creation, which basically lead us to these three ways that we have right now for encoding domain models. So the old way in which you have a domain expert and a planning expert, some machine learning technique, and then some crowdsourced techniques. And yeah, I think it's basically time to wrap up what we have seen. I'm not going through all the aspects that we have touched today, but I will just do a very short one slide conclusion and then highlight some challenges that we may face in the future. So the main point that I think we emphasized is that the domain model is the cornerstone of any planning application or of any use of planning. Let's say that both the domain model and the planners are extremely important, but since there is a huge availability of planners, in here we focused on the domain model. And the problem of a domain model is that it is stretched between these two almost antithetic perspectives. So on the one hand, you have a human which is encoding the domain model and which wants a model which is readable and which carries some information which can make it easy to validate and to maintain. And on the other hand, you have a planning engine which doesn't care much about maintenance of human readability, but which just care about having something which is easy to reason upon. And these two perspectives can somehow be merged in the sense that since we have decoupled the domain model from the planning, we can put them together using domain knowledge. So you have an initial model which is human readable and which has all the characteristics and properties which made it okay for a human. You reformulate it in some way, and we have shown some way for doing this reformulation. You provide it to the planner, which will then be happy to reason on this planning friendly form. And you can have different way for extracting the domain knowledge. The one which mostly support this kind of interaction is clearly the automatic extraction, because in that case you don't need to do anything. You have literally just your domain model which is reformulated and then used straightforwardly. And the last point that I'd like to raise here is that the fact that we are giving very little attention to the knowledge engineering of models, while we are giving a lot of attention on the planning side. And finally, for raising or for highlighting some challenges for the community for the future in terms of planning, I've just put together some food for thought, really, where there are no solutions right now, or no solution that I and we are aware of, but it's just a matter of throwing things out and see if that raises some interesting, let's say, future work or future development. One point is there are tools and there are techniques for handling domain model evolution and validation. There has been also a couple of works in the recent years in this direction, but they tend to be extremely specific, so they tend to restrict either to a given subset of PDDL or to some given scenarios and domains, while we don't have some, let's say, wide applicable and very general techniques which can support, also from the point of view of the encoding, let's say, the model's evolution and validation. Specifically, the evolution received very little attention. And what we already raised before is the notion of quality. So we don't know, given two models, we don't know how to compare them, and we don't know how to say that one is better than another one. And we don't know if the notion of quality must be statically assessed, it's dynamic, or must be related to other aspects like the context in which you are using it, or the planning that you are using for solving it, or some different aspects. Cooperation in knowledge engineering tools is another aspect which should gain attention, and which is becoming important right now, given the complexity of the planning applications that are now deployed and which are now being distributed and thought about. And finally, another idea which was basically discussed yesterday at the knowledge engineering for planning and scheduling workshop is the fact that in object-oriented planning we have what is called design patterns. So we know that in order to encode in an object-oriented language some behaviors, there are some ways which can be studied and which can lead to very good results in terms of readability, maintenance, and etc. Can we do something like that also in planning? So can we think about every time in which you have, I don't know, a board in which you can slide pieces, these sort of operators or these sort of predicates are needed, or every time you have some domain in which you need to move between different locations which are connected, this sort of operators and this sort of predicates will be needed. That's probably something we can think about, and I don't think it needs to be focused only on PDDL, but it can be at a higher level language, which can then be grounded, let's say, into PDDL. And yeah, I think that's all, and that concludes the tutorial. So thank you for attending. I think okay, if you have any question, we are here. In the meanwhile, we can just show the, I don't know how many references we have here. Quite a lot. So yeah, anyway, we will provide it via the website. I can't believe how many references we have.
It's a tutorial, that's right.
And yeah, here we are.
Any questions?
Yep. Yeah, so I mean, this macro generation technique, I mean, using say MAP or other techniques that you have shown, it could be inefficient for the planning process just because, I mean, in some cases, when the number of arguments or the number of instances are very large, because of the explicitly defined the number of arguments. So I mean, just wondering how about using the existential quantifier in the precondition of the macro action, or using some Christian type hierarchy among the macros. Is it beneficial, or I mean,
Yeah.
do you think about that?
That's on you.
I mean, well, the thing is that, let's say, if we assemble macros in the, let's say, straightforward way, so we need a lot of parameters, so which clearly provides a lot of instances. So, I mean, clearly, one thing is if we have planners that are lifted and they don't do grounding, so that it might work. The other possibility might be somehow to take some parameters away, because I mean, you know, they can be somehow internal. So I mean, for instance, if you have a robot with two hands and you just carry one object from one place to another, and you know, you might not care about which hand you use. But I mean, technically, if you assemble the macro in the straightforward way, you still, you know, have to have that information. So I mean, that one thing. And you know, just, you know, to remind our joint paper about using block decomposition for macros, where actually the problem was if we had some larger block, which I mean generated larger macros, so that, you know, the number of parameters and the number of instances was a problem. So I mean, actually, in one case, so it was still better because that macro was really very informative. Yeah.
Yep.
Yeah, in many industrial applications with complex interactions, people in the industry often use some kind of deep learning techniques which are very trendy, you know, to acquire, knowledge, but without any symbolic view of the knowledge, and then produce plan on the basis of this knowledge, like AlphaGo a bit. So I was wondering whether there were attempts to trying to translate this deep learning knowledge to something more symbolic, that you can reuse and exploit with the current planner techniques.
Right. I think this is actually a very good question, because I mean, recently we were talking with colleagues about this. The problem is that, you know, approaches like AlphaGo, where you have the deep learning, so then, you know, you provide some information, then it somehow does some magic, and, you know, it gives you a result. So the thing is that you do some training, you learn that, you know, deep neural network somehow, that you simulate, I don't know, billions of games, and then, you know, there is some information that is stored inside of neural network, and which at the moment we don't know actually how to extract. Because how it works is that, you know, it takes the current state of the game and it will provide the next move according to some knowledge the neural network has. And I mean, for planning, so actually there were some attempts to use machine learning to generate a domain model from, for instance, plant traces. That you know, still what you need to get is you need to get that symbolic representation somehow. I mean, from the neural network you just don't know why it works. So which, I mean, in future, I mean, it is quite a good research topic how to basically get the model, because I mean, in fact, that planning can guarantee something. You know, because, you know, if let's say the assumptions of the models are followed, so you provide a plan and you will always achieve the goal. Well, in that machine learning is more like, well, you somehow learn some information and you see, okay, I am in a certain situation, that probably best move is this. And I mean, for games like Go or even poker, for instance, that, you know, it's usually sufficient. But I mean, in some, let's say, more complex systems where you need, let's say, some sort of validation, verification of the process, where you have to know what is going to happen. So that you need some symbolic reasoning, so that you need to have a really like domain model, you know, some symbolic representation, and then you can do some reasoning, so that you can check that, for instance, I mean, this can't happen, or well, there might be some situation where something can happen, so the model should be improved, and yeah.
Just to complete on this point, there was yesterday at ICKEPS, and I think they will also present it at the main conference, a work from Asai and Fukunaga, in which they used deep learning for learning from an M-puzzle scenario, how basically which sort of actions you can apply to the scenario in order to, give an initial state, get to the goal state of M-puzzle. And there were, in that case, some attempts to generate also the symbolic reasoning, in the sense of, okay, I've learned, because they were provided as training instances, couples of scenarios showing the initial, let's say, state, and what happens if you apply an action. So from this sort of knowledge, which was this sort of training knowledge which was provided to the deep learning system, they were able to try to generate some PDDL actions, which were not extremely well engineered at that point, but I think this is also a step in that direction. Cheers.